Okay, so this is video 4, lecture 3, and in the previous video we created this equivalence between the bin model and the learning model, with the bin being the input space, the difference between the target function and the hypotheses, defining our green marble and red marble, and the fact that we are randomly picking a marble is compared with the probability being random, right, unknown to us as well, was able to establish that there is a relationship between a bin model and a learning model. And above all this, like with this equivalence, we were able to also convert the Hovding's bound, or the Hovding's inequality, I would say, to the learning problem, right? So if you just remember from the previous slide, this is how the Hovding's inequality can be summarized. So instead of the nu and the mu, we'll have the in sample error and the out of sample error, because that's how we established the equivalence, right? And this is the probability of the difference between the in sample error and the out sample error being determined by the tolerance that we're going to set before, and the rest stays the same. The right hand side stays the same, right? Depending on the tolerance and the size of the sample, we can come up with this bound. Okay, so having said that, let's move on. Now, we know that we don't have much control over nu, right? Which also tells us until now with this problem, we don't have any control over our in-sample error. In-sample error is essentially the difference, or the in disagreement between the hypotheses and the target function. That's what we defined it as. Now, having said that, when we looked at this problem here, what we did was we fixed a hypothesis H, right? We began with drawing that line here, this H here, right? And then we said that once we have this hypothesis, we determine the red region and the green region, and then thought of like how, like, the red region and the green region will determine the in-sample error and the out-of-sample error. Now, if you think about it, this is not really learning, but it is verifying. This is called verification because we are simply testing whether my H is good or bad, right? So what we want to do here is we want to establish the difference between verification and learning and see if still all the concepts, all the ideas that we have built until now, they still apply to learning. Okay, so what is the difference between verification and learning? We can tell that by actually writing it down. What we did just now is that we fixed a hypothesis H, and obviously before looking at the data, and that was our final hypothesis, right? So that's of course a part of verification. We fixed H, right? And this is a hypothesis. Now what we did in learning, and by the way, this is verification, okay, and this is learning. What needs to be done in learning is that we fix a hypothesis set, if you remember from one of our earlier lectures, right? So we fix a hypothesis set H that can have multiple hypotheses in it, and our goal is to sort of fix that final G, if you remember. Okay, so the goal in both the verification and the learning problem is that we need to certify whatever we have as good or bad, right? So here we certify H, which is of course good, right? H is certified whether it's good or not. Here, like in learning, what we do is that we pick a particular hypothesis G from H, right? So pick, maybe I can say pick G that is a part of this H, right? And then obviously using the data. Now we are using the data here, so we have to be a little more cautious, right? And then use the same data to certify G, right? So then again, we want to certify G. So that's again a part of learning. Certify G, whether it's good or bad, using that data, right? So basically pick a G that looks best on the data. Looks best on D. Okay. Now, here we saw that H does not depend on data, right? It does not depend on data because we picked it before actually looking at the data, right? So it does not depend on the data, but here G depends on data, right? G was in fact picked from the data. Okay, so what this tells us is that once we're done with like whatever we're trying to do. What we want to do in both the cases is that we need to have this relationship of E in calculated on H to be as close to E out calculated on H as possible, right? And we want this to happen in both scenarios, in learning and in verification as well. Now, because we fixed E like this H before we calculated anything here, we actually have no control over E of n here, or the in-sample error, but we do have control over in-sample error here in learning. And how is that? That's because we eventually picked the like our G, our final hypotheses, based on the value of E of n, right? If E of n was small, if this was small, so we picked En of G. This is what learning means, right? So in order to achieve that, if you remember, we have something that's known as the Hofting's bound, right? Because Hofting bound gives us the bound that this comes really close, or nu comes really close to mu, or the in-sample error comes really close to out-of-sample error. And we can apply that in verification. So we can apply, I will just write, we can apply Hofting's bound to verification in this case because we fixed our hypotheses set, sorry, our hypotheses H before looking at the data, right? So we fixed this here before we looked at the data. Now, we want the same thing here. We want this E of n, which is this, to be as close to E of out, which is the out of sample error calculated on G, as much as we can, right? So we want that. But remember, G came out of the picking process, right? That's what we said, that's how learning works. We have to pick one G from the data that we have. So we cannot apply the Hofting's bound because the assumption under that is that we cannot look at the data before we formulate G, right? So we cannot apply Hofting's bound because we are using data to pick G. So this Hofting's bound cannot be used in learning, at least in the way it exists right now, right? So this is the fundamental, I would say, takeaway from verification versus learning as far as we know it at this point. Hofting's bound in its current form cannot be applied. And if you think about it, what's going on in here, like when we are picking G, can be actually visualized here. And if you're looking at this picture, what I'm trying to do is I have like these different hypotheses, and consider these as bins, right? So these are my bins, all of these. And remember, just like we picked H, we can have an H1, H2, H3, H4, and so on, up to H of M. And this is like my entire data, and these are my samples. So those are my bins, these are my samples, and I can calculate my E of n, or in-sample error, for every hypothesis, right? And then what I'm trying to do in the learning process is that I'm trying to pick the E of n as small as possible, right? So that's because that's the best thing that I want to do, right? I want to like minimize my error or make it as small as possible, right? And so I'm going to pick up the one that has the smallest error, and that kind of is what I'm trying to do in learning, at least as of now. Now, because my E of n is like really small, can I say that E of out will also be small? Well, if we can look at this, can we say that the probability of like picking a red marble is also 0 in this case? I don't think so, right? That's not really the case. So basically what we're trying to do is, if my G, the hypothesis that I finally picked up, is H2, right? Because H2 gave me this 0. Are we able to certify that this is like this G is the real approximation for my target function? We won't be able to conclude that, right? Because what we have done by doing this like sampling from and coming up with different hypotheses and calculating the in-sample error is that we have biased our experiment, right? We have biased ourselves to choose the smallest in-sample error. What does that mean? Well, the ability to choose, because we had the ability to choose, which we did not have in the verification process, first of all, came with a price that the Hofting's bound did not apply. And the reason for that is because we have like this selection bias in our process, right? So we have introduced something that's known as selection bias, this is a very common term in especially the medical results, where sometimes the sample that you take out of a population is biased. Let's say they were healthier individuals and the test that you're doing is for some particular age population, certain race or certain gender, and so the results that you get are really biased based on the selection process of your sample, right? And this is exactly what's happening here. And so we cannot like say that E in, because E in is small here, that E out will also be small, right? Just by looking at the picture, you can tell that's not the case. And so this selection bias, as I said, is a common problem. And obviously we have to come up with something in addition to what we have in order to be able to like justify the use of E in for E out under the learning process. And we're going to talk about that in the next lecture. For now, the key takeaway here is that, like, let me write it down, the notion of choice, right? The notion of choice when determining or when selecting G, right, gave us the ability to establish like that, to get E in of G to be like really almost equal to 0, but we cannot apply Hovding's bound, so we cannot say, or let me write it down, cannot say that E of in is almost equal to E out, right? So we cannot say that. And this is something that we'll dig into in detail in the coming lectures, like how can we establish a relationship between E in and E out. And now we know that this is a selection bias that exists, and so the learning problem, although we have translated it from the bin problem to from the bin to the learning process, not everything is what we would like it to be. Okay, so with this, I would just like to end this lecture. Thank you.